Hi students, welcome to Science Extension and Module 3, the Data, Evidence and Decisions. This is video number 16. We're going to be looking in a little bit of detail at the correlation coefficient. Our student learning outcome is that you can apply statistical tests that can determine correlation between two variables, including but not limited to the correlation coefficient. So correlation is a measure of the degree to which a series of scores on two variables correlate. In Hinton's words, the extent to which a variation in the scores on one variable results in a corresponding variation in the scores on the second variable. One of the things that's very important, and we are going to try and draw this distinction at some point, is between correlation and regression, and I will talk about that a little bit more in the next video when I talk about causation. For now, instead of comparing means or variance between different samples as we have with some of our other tests, what we're doing now is trying to examine the relationship between two different groups or two different variables to determine the degree to which they correlate. The simplest way to do this is to create a scatter plot, and then from our scatter plot we draw a line of best fit. Now remember, that line of best fit doesn't always have to be a linear relationship in the form y equals mx plus b. It could be any mathematical relationship as long as we can see some sort of consistent pattern that follows one of those mathematical curves, then we're probably okay to talk about correlation. However, the most common types of correlation coefficients that you will be calculating really do fit that straight line relationship of y equals mx plus b. The closer the values are to a straight line, the stronger the correlation is between the two variables. The important thing about correlation is if you think you might have a relationship that is more of a parabolic relationship, y equals x squared, for example, then instead of plotting a curved graph of a parabola, it might be better when you're testing your correlation coefficient to plot y versus x squared rather than y versus x. And that again should give you a nice straight line. So when we look at our data, the important thing is that there are some other questions we can ask other than just what do we know about the means and are they similar? What do we know about the variance and are they similar? What can we tell about observed patterns in relation to expected patterns or values? So this is what we've been asking up to date with some of our other statistical tests. But now we want to know whether two variables are related to one another. And we can use the Pearson correlation coefficient in order to do this. We can also ask whether there's a relationship between a range of different variables, and this leads us into an analysis of variance, or an ANOVA. Now, the one thing that's important to note about the ANOVA is it's a very good and a very powerful test, but it's not specifically mentioned in the syllabus. So I don't think you would need to use it. The only reason I would suggest it here is depending on the nature of your own research study, you may find that exploring an analysis of variance may be relevant to you. So we calculate our Pearson correlation coefficient and then we get a number, and this number is going to range from -1, which is a perfect straight line indicating a negative correlation, 0, where all of the data points are completely random, there's no pattern in them whatsoever, or +1, which is a perfect straight line indicating a positive correlation. So the slope of that particular line will be different and it'll head up towards the top right as opposed to down towards the bottom right if we are plotting these on a graph. So we can get a sense of the nature of the correlation or the strength of the correlation by doing a calculation of what's known as the Pearson correlation coefficient. Now, you'll often find the abbreviation for these in the tests as Pearson or as Correl or correlation, and these are the ones that you're going to use, and you just need the two sets of data in order to plot these and then calculate this particular value. Now, what I would do is I would make sure that you plotted the values first, so you've got a little bit of an eyeball test as to how closely the data fits to a linear relationship. And then when you put your Pearson correlation calculation into play, then you can actually confirm or deny what it is that you think is going on from your test of the visual distribution of your data points. Now, it's fine if you get a value of -1 or 1. actually it's probably not fine, because we would be very suspicious of your method if you had an absolutely perfect correlation. Usually you're going to find something that's less than 1 or slightly more than -1 if you've got a negative relationship. So we need some sort of cutoffs. Now, some of these are arbitrary, but generally speaking, if you've got a value of greater than 0.7, so between 0.7 and 1, that's indicating a very strong positive correlation. Between -0.7 and -1, you've got a strong negative correlation. If your correlation sits between 0.3 and 0.7, or -0.3 and -0.7, then you've got moderate positive or negative correlations. And then if it's between 0 and plus or minus 0.3, then we really have a very weak correlation and not really much we can talk about in terms of the relationship between the variables. So how do we use the Pearson R? Well, some interesting data that I've just shared with you here on kangaroo snouts. A student wanted to determine if there was a correlation between the nasal lengths and nasal widths of kangaroos as part of a study of adaptations to dry, hot weather. The student measured the lengths and widths of the animals' noses and recorded the following results. So here's our set of results. Now, when you look at these results, it's a little bit difficult from the eyeball test to determine whether there's much of a relationship. However, if I transfer this information into Excel and get Excel to create a scatter plot of this data, then you can see my distribution of points. And here are all of my data points. I've got a little cluster up here that's kind of looks like it's not quite sitting on the line. But if I ask Excel to draw a trend line, so just put in a linear trend line for me, it's putting a line in that's relatively close to these. They don't look completely random to me. So when I'm looking at it, I'm expecting some degree of correlation between these two variables, nasal length and nasal width. Could I actually do something with this though in Excel? Well, yes, of course I can. What I can do in either Google Sheets, that's the Google one, or in Excel, I can use the Corel or the Pearson to put in the two different sets of data, the two ranges representing the array or matrix of the dependent data and the independent data. And all I'm looking for is a relationship between these. Now, which goes where doesn't actually matter when you're calculating your correlation coefficient. It's going to be the same value either way. It is going to be a little more important when we talk about regression later on, but you can see the simple way to calculate this is just to go into my statistical functions, select my Pearson, and you can see when I select Pearson, I get these values here. I put in my two arrays, which are B1 to G1 and B2 to G2. So they're my two sets of data. And you can see, once again, coming out from our little box, before I even click the OK, you can see these numbers coming out at 0.91. So they're very, very strong correlation. So there does seem to be some correlation between these two variables. Now, the only other thing that I probably should mention at this point is that there are reasons why you might also calculate the R-squared value. And sometimes you'll actually notice in the papers that you've been given that there might be an R-squared value. So what's the relationship between the R value, the Pearson R correlation coefficient, and the R-squared? Well, obviously, R-squared is just the square of the Pearson correlation calculation. And what the R-squared does is it measures the proportion of variation in the dependent variable that can be attributed to the independent variable. This time, because we're squaring it, we're not going to get negative numbers, so we're going to have everything sitting between 0 and 1. And what that means is that we can talk about this, we can convert this decimal into a percentage, and that makes it easier for us to calculate the relative variation that can be attributed to the independent variable. If we see in this case that we're looking at variation in nasal width, then by squaring our R value, we get a value of 0.83, which is about 83% of the variation in nasal width can be attributed to nasal length. It may well be that you want to have a look at your data just visually by putting it into Excel and drawing a graph. You can get a bit of an idea of the way that the data is distributed through a scatter plot. But once you've done that, you probably do want to have some more specific measure that you can use to evaluate what you're doing. And the Pearson correlation coefficient is one good way of being able to determine the degree to which the data correlate. But correlation does not necessarily imply causation. For that, we're going to use a slightly different test, and that's going to come up in the next video. Thanks for watching.